It's going to start bringing in some of the concept of the deformation processing. When we weld, we essentially generate a new casting. And then, I mentioned a few times that welding is used a lot in fabrication, mostly for the reason of cost. And there are certain geometries that we wouldn't be able to do other ways. So we'll go back. Last time, on Monday, we started going over a little bit the fundamental that you have a fusion zone, you have a toe, and you want a penetration. So we'll go back to that a little bit. But then I want to have essentially a discussion around two main topics. One is welding for low strength applications, so building and other structures that are not very highly demanding, and then we'll do the case of something that is more heavily loaded at the end. I didn't bring parts, I have a video instead today, so that should be fun. So this is the image we used for the introduction. Just wanted to go back to it very quickly. So the word fusion welding just means that, we're reaching a point where there's enough energy to melt the material. What I mentioned last time, that is the most significant challenge with welding, is that you have to protect the molten metal against oxidation at high temperature. So in the most basic process, we use a shielded electrode that also melts and forms that slag on the surface. So one way that that people have used a shielding electrode or a slag is, after the welding is done, it looks really bad because you have that slag that is covering the actual metal. So people have to hammer it down or brush it down to actually have the bare metal and then do the painting. There are other processes. The main alternative is to use a gas, that you shield the area of the welding with an inert gas or a reducing gas. And in that case, you don't need to do any cleaning. And that's what you do in automotive, for example, or the semi-automated welding processes use a shielding gas. One thing that we try to promote, this is something I brought in when we were talking about the deformation of of metals. We were saying that, especially in forming, we try to avoid tension, because if we have tension, we tend to form these microvoid in the material. So all the rolling processes, the forging processes are intended to bring as much compression in the material as possible. So here we have the opposite case. Unfortunately, a lot of welds are loaded in tension, materials are loaded in tension, and to the extent that you're able to avoid any effect of the environment, what you'd like to have on the fracture surface, this is looking down on a crack that's separated, is a ductile mode, which is essentially a number of dimples. So if we were trying to do a profile of this surface here, it will pretty much look like this. It's just a little ligament. So essentially half holes into the material. There may be some bigger ones that are the origin of forming. Essentially, you had an initiation of a little void in one area. In this schematic, it started at an inclusion. So you have a hard piece of material in the material. You start deforming it. It debonds at those locations. It stretch. You can see that if we started in contact here, when we get to this point, this is where we get our 200% strain. The material becomes about twice as long before it fractures. That's the ductile behavior. Now, why it breaks is not so much because of this stretching. Well, there's a little bit of this, but the other aspect is it runs against another little microvoid that was next to it, and now you only have a little ligament to hold the entire load, and it necks. So anytime that we have a fracture on steel, and I'm not kidding, this is very, very common. The first thing people, because you have to go to a high resolution microscope to see these, The first thing people want to know is, did it fail in an overload in a ductile way? Because if it did, it means that you reach the material capacity. But there are a lot of other ways. If it happened in cyclic mode, then you don't see those features. If it happened because of environmental effect, cracking, embrittlement, you don't see this. So, I have an entire module on interpreting fracture surfaces, but for our purpose today, what I want you to keep in mind is, if there's nothing wrong with the material, when you load it in tension, it should deform significantly before something else happens. And we'll go back to an example where that didn't happen. So the first simple example is a greenhouse I worked on. That was probably 10 years ago. So it's easy, I can talk about it all day long. They resolved all the problems. It was about 25 acres. So you couldn't see the end of it. It's indoor. The design, just so you know, was essentially intended to provide enough heat to the windows and the ceiling to melt the snow as it falls. It's a pretty audacious assumption if you're up in Maine and there's a big storm. So that's a little bit what happened. There was, a little bit of snow accumulation. The water couldn't drain completely. So there's a little bit more load than what they anticipated. But the main issue and the reason why it actually broke are these joists that are essentially the main structure connecting. So the joist connects these columns to the entire roof structure. So a typical joist get an upper chord, a lower chord, and you see those anywhere you go into a Walmart or at the airport or a warehouse. So upper chord, lower chord, and the diagonals is the image I was showing you on Monday. These are solid rounded piece in this case, and one reason is it's very inexpensive. It's cheaper to buy a solid round bar than to buy a tube, and it's easier to form. So the diagonal, what they do is they take the solid bar and they form it this way. So there's enough lap with the chord here to make the welded joint. It's a very, very simple design. I'll show you a more of a close-up view. Not here. Well, you see better the diagonals going up and down. Those are essentially transferring the shear load between the two chords, and you can see them in detail here. So we have a diagonal coming down, we have a little weld here, and then we have another diagonal going up. Just for weight and cost optimization, they had the diagonal in compression bigger than the one in tension. So we can already tell that the smaller one here is the one in tension. What do you think of those welds? Don't know? It looks like a caulking job, right? So it's probably the main thing I want you to get out is if you have a joint, and we'll just make it square here for our purpose. And when you put the welded bead, it kind of looks like this here. It's very rounded. It's pretty much as if I just put the material there. So it's not likely to have a lot of fusion, as opposed as if it looks like this. I'm taking an extreme case. This is pretty ideal, or actually it's probably too much heat. But when you see something like this, you just have to think of surface tension, because it is something that's melted on a solid surface. So if you have the base metal that's very hot, it's going to have good affinity, and you essentially will be able to spread your fusion zone further away, and it's a smooth transition between them. If you have the opposite situation where the base metal is not completely heated close to the point of fusion, then the bead just pretty much stand on it and try to be as small as possible. So just visually, and there is an ISO standard for this, just visually, that's how, by inspection, you can make that determination. Do I have all the fusion or not enough fusion? So going back to this example with the bead here, you probably see it on the profile that it's very rounded. And the criteria actually is, if you reach the 90-degree here by any standard of welding, of ISO, even the porous, you fail that criteria. Now, if you go to the gym and you look at the equipment out there, the welds are going to be pretty close to this. And just so we all understand why that happens, is they're welding pretty thin material. So we're talking about something that's about just 1/8 of an inch, and they're putting a big weld on it because they know it's at the corner, so they want a lot of material. So if they were to make what I would call a good structural weld like this, well, a good one is going to have a little bit more an angle. Let's put it almost straight for now. That's perfectly acceptable. If you were to do that, you get too much fusion into the material here. So if your thickness is only this way, it's called a burn through. That's not good, because now you have to go and fix it again. So when you look at all that equipment, they're thinking about, just making it look very consistent. They also know that they have a lot more weld metal than they need for strength. So there is a little bit of an understanding that if there's not a full fusion for a little area, it's going to be acceptable. But the process needs to be very optimized, because if you go from almost vertical to what we call an overlap, so the overlap defect is essentially the bead that's going to extend and have a slope going the other way. That is a big no-go, I would say, even for the fitness equipment. So I think hopefully it gives you a little bit more of a perspective of why we are able to judge the fusion. One thing that you'll find a little difficult if you end up having to deal with welding contractors is it's not in American codes and standard, in AWS, they don't specify that angle. It's a judgment. I have to say, as the welding inspector, there is a problem with your fusion, or it's fine. It's a very qualitative judgment. There are criteria in terms of the convexity of the weld that I may be able to use sometimes. So if it's really rounded this way, you also are too convex of a weld. So there is a requirement for that. But in terms of just knowing that you may have a risk that you did not fuse your base metal, it's a little bit left to the inspector. Now, after the fact, it's very easy to do. So if we look at a joint like this, when it failed, the easiest way to identify the lack of fusion is this is the original shape of the tube. There's nothing that happened to it. So the tube is hollow, just like this, before and after. So the welding that was over here is just gone. And with the paint. Yes?
Are you concerned with burn through the hollow part?
Yes. And you will see that in that section. That's a very good question. So one reason, and this is on the repair. So this whole process is, they had a little bit of an overload, not big of an overload. Then they called on inspectors to look at the weld, and every inspector said these welds are not good. You shouldn't be using them because they won't behave in a ductile way. You never know when they're going to snap, and therefore they're not reliable. Now, on the repair job, we still had some defects. So this is one example. So we have the rounded bar, and the welder, you can tell, was trying to put a lot of the heat into the round bar because that's the biggest sink. This layer here that's pretty much where the tube ends. So Yeah, so that's the end of the tube here. So if he had put the torch and the heat in this zone, he could have had a burn through. So he's trying to avoid a burn through to some extent, but just a little too much. So here he just went too far into putting all the heat there, and he was going to essentially have the same type of field failure. Here it was more of a compromise. So probably 2/3 of the heat or so on the side of the big bar, and then 1/3 down. Now, one thing to keep in mind, this is repair welds that we had them do so they could continue to operate. It's not all clean, right? I think the fitness equipment will show you a much smoother weld profile. So essentially, we see the evolution of the melted pool as we were moving forward. It's going this way. At every point in time, the fusion zone starts to solidify and leaves you a mark behind. I brought in this image just to emphasize that this is not a problem. Okay, the idea that there's a little bit of a surface profile on the weld, a lot of times is actually a good sign. This was the best welder they had there. He used to do a lot of high pressure vessel, and you could tell he was weaving a little bit. And that's what you need to do for this type of joint, because the two pieces are pretty apart from each other. So unless you purposely transfer the heat on one side and the other, if you try to put it just in the middle, well, that's not where you're going to weld anyway, so something else is going to happen. So I was actually telling the younger welder, I said, look at him, look at what he's doing, because it wasn't excessively hard, but it made all the difference in terms of passing all the qualification tests. Yes?
What kind of welding was done here?
This is just regular structural steel, so pretty low strength steel.
Or, I mean, like, is it MIG, TIG?
They were doing just regular stick welding. And the reason is the structure was galvanized, and they were cleaning up the galvanizing, but it was very difficult to make sure there wasn't any paint left or any galvanizing. So the two main options were the shielded middle arc welding or flux core. But the people were not very familiar with the flux core, so you have to go with local preferences sometimes for this. So what else? You can see that they've put on multiple beads. So over from here to here, it's a different orientation. It's a different pass of welding than down here. And that, of course, will help in terms of filling this entire area, because you have to keep in mind that we have this bar here, and there's just a lot of space, and you can't get all the way to the center. So all you can do is fill that space here. And it's called a flare bevel groove weld. It's not the most common, but it's used in large quantity for cost reasons. Now, this project with the greenhouse, the joists were made in China. They were selling them very, maybe 20% more than the cost of steel. So just trying to repair the joist on site was going to cost a lot more than getting new joists. So they made a little bit of a calculation, and even though it required to disconnect all the electric and a lot of plumbing into the greenhouse, they replaced every single joist one by one. There were 2,800 of them. And the bottom line in terms of quality control is this joint cannot be made perfectly all the time. And therefore, as far as the repair welding, the simplest instruction to the shop was welded both sides, because on the original installation, the design engineer calculated that a weld on one side was sufficient, but it caused two things. There's no redundancy, and then there's also eccentricity, so a little bit of a twisting action on the joint. So it was, in the end, a pretty successful project. It took a while to convince the manufacturer. So even though the joists were made in China, The owner did not buy them directly, so it was essentially provided as an entire system. And the people that provide the system, there were only 3 of them that really do that in worldwide, like big companies to provide greenhouses. So they did want to hold to their reputation. They were very responsive, but they didn't like the idea of taking everything out. So they really wanted to repair in place, and we had to let them do it a little bit so they realized how long it was going to take. And then finally move on to get new joists. So we had a lot of shoring activities in the meantime to hold everything in place. It's just not the best word, and it ties a little bit to, in terms of factor of safety, buildings do not have a huge factor of safety. So anytime something is not done exactly the way it's supposed to, then you can have a problem. I have other examples because I don't want you to think that the joists are all made this way. So here we essentially have an angle, so a flat piece of steel that is bent 90 degrees, and it's crimped a little bit near the end. So instead of being a 90 degree here, it's squeezed a little further to fit between 2 other angles. So in design, and that's actually right now one of the most prevalent design for joists. So it will look like this. You have an angle here, you have another angle here, and then you squeeze in the diagonal. So this is the lower chord, and you have an upper chord. What you're looking at here is this diagonal. It's very difficult to weld, so you have to come and weld between the 2 other pieces of the cord. So difficult to make a good quality welding, but in terms of manufacturing, the number of pieces that you have to put together and the speed that you can do that's the prevalent way. So the only caution, the only way they manage to do this correctly is by putting extra welding. So it's welded both sides, assuming even if one side is incorrect, the other side is going to pass. But the problem with this manufacturing, there's so many welds that the idea that an inspector will go through every single one of them and say, oh, you missed on the left, oh, the right is good, okay, we're good. So a lot of times what I've seen is they're going to have a different diagonals at the end here. So they'll have all these little things going on, and then this one is going to be solidly welded to both sides in shear. Like it's really like 2 straps coming down and welded fully, because they know they may have some of these that will let go, and they don't want, they want to prevent a collapse without a doubt. Yes?
So instead of having a separate inspector, wouldn't it make more sense to train the welders so that after each weld they self-check?
That's a very good comment. So the code allows for that. It's the AWS welding code will say that the inspection belongs with the welding contractor, and it doesn't say that the foreman has to look at every single weld. So I think that the assumption is that there will be some oversight, but that the welder himself is supposed to know what he's doing. One thing to keep in mind when it's semi-automated like this, it really goes fast. Like one side, then you move on, you do the other. So the time that the welder takes to actually look at what he's doing each time is not always clear. And again, a lot of this is done overseas, so exactly what they understand is the criteria is also a problem. But in general, it's not a problem. That's what it happens with failure analysis. I'm showing you a few example of things that can go wrong, but we had so many ice storm and snowstorm over the past 3 or 5 years here that by now we know that it's maybe 5% of the main building built in a certain year range that were not really as good as the code said. Everything else fine. But it comes out at a big number. There was a lot of consequences to it. But you only know if you have the right safety factor when you load it to the maximum capacity. So that's really something we've learned. Now I'm showing a few different things here. So this one is different. In this design, you had the core, and it's a tube, a diagonal tube, a square tube that was coming into it. And hopefully you can see here, it's the same situation where it's the original surface. Now there's a little bit of fusion here at the corner, and then there's a little bit of fusion there. Now, this particular design, the welder had no excuse. This is easy. This is supposed to be easy to weld. You just have a square joint like this one. So they were essentially having too high of a feed rate, providing too much metal for the heat, and not fusing sufficiently. It happens over and over. I think I had a little summary sheet. I've looked personally at maybe 15 different roof collapses in a period of only 1 or 2 years when I was working for a structural engineering firm. There was one case where the size of the member was insufficient. Everything else was an issue with the joints. And what we've learned over time is in that industry, they don't consider the welded joint that important. They spend a lot of time in their calculation figuring out how much spacing they'll have between joists and what's the size of the members, and then it's pretty much left to the shop to make the welding that needs to be done so it all holds together. So it's unfortunate because, again, the pieces that get overloaded in the end are the joints. Here you see physically, just looking under the joist, the separation. So I have that angle, looking at this angle, and I have a solid bar that fits in it, just like this, and they started welding it, but they did not get the fusion on this side because you see the gap right there. So it's the most unfortunate aspect to this. That's another one. And we had to use boroscope and all sorts of ways to try to see everything everywhere. And so the place that they grade the final exam for high school, and season was coming up, so they had to operate. And it's just a big problem because you go through the entire facility and you can see, so the orange color was everything that needed to be fixed quickly. So I guess maybe one take home from these examples is you do want to say the quality that you're expecting to have, and if it's relatively important, you do want to make sure you were provided what you asked for. It's a lot easier when the pieces, especially pipes, if you're building a facility with pipes, when the pipes just arrive, it's easy to say, no, I don't want this. So receiving inspection is very highly recommended by the code. It's not required. So it's one of those areas in the industry where people do different things. So there will be people that have had issues in the past, and they will look. And there are even a lot of people that contract manufacturing in China have people full-time going from one shop to the other to make sure that the processes are always in control and that the inspections are being done and the quality is what it's supposed to be. It's very common for shipbuilding. So if you I don't know who is really rich here and wants to buy a big shipping vessel. Anybody? Okay. Because we can always sell you something else if it's a shipping vessel. So if you have that industry and you need a certain fleet of shipping vessels, and next year you want 2 or 3 more, you get them built for you. It's nothing like you go to the store and buy whatever is there. So they build custom, and even though there's a series of international standards for quality on the material to use, the joining to be done, they have people on site full time. This is not like, I'm going to take a trip, see if it looks good. So they have people full time to make sure that the procedures are followed and the inspection is done, because when it's all built, and they start to use it, it starts cracking, it's become their problem pretty quickly. They can't, all of a sudden they have backlogs, they have to find another vessel to use from the time this one is in the dry lot. So I'm using ships as an example. I think almost everything. I mean, you build it and then you want to use it. So the idea that you don't specify clearly what you want on the first place doesn't make much sense, but believe me, it's done a lot. So it's not uncommon that you're going to have even something pretty sophisticated and then you send it for fabrication. You say, oh, I want this size weld with this type of electrode. Okay, I'll do that, So the most common thing on the drawing is it's going to say, use a 7018. That's the most common type of electrode for welding steel. Okay, I do it the way I want then. So what you want to do is say, and I'll write it down. So you have the qualification, you have the fabrication, and you have the inspection. Those are all important. By code. Decide which code you want. There are a few. AWS is very common for buildings, but there are other industries that you're going to want API. There are industries you want ASME. It does depend. But if you don't do that, I mean, you could write your own spec and say, this is what I want you to do. This is what I don't want you to do. But if you don't, it's very hard, especially if it's a general welding shop, to expect them to know what kind of quality you need for your application. So I hope I emphasize the kind of the quality aspect. So now let's move on to some of the inherent weaknesses of welds. We have two main categories. The butt weld is typically done with a surface prep. So instead of having two flat pieces together, you put a notch in them. So you remove material. You can remove it from the two sides, although what is most commonly done is to essentially have a flat piece on one side and you bevel the other one at 45 degrees like this. And then you start filling in your material until you have a joint. Now, we can probably see right away that when this is done, and depending on the quality level, the root here can be done from the other side, or it can be ground flush, it can be shielded, you can put a backing bar. So there's just a lot going on here, because these joints, a lot of times, especially if you're building like a nuclear structure or something that is going to be used in a very reliable way, you can make these joints have the same strength allowable as the base metal, if they're done completely correctly. Not in fatigue, just for the static strength. Because there's no stress concentration, and we'll see later that there's also very little residual stresses. So this is probably the strongest joint you can have. And from there, we'll see worse and worse and worse and worse. So, one typical joint that is a little bit more of a problem is, say, I have two members here, but somehow I'm not really able to connect them other than by putting a weld here and putting a weld there. So this is a lap joint, but I made the lap, if my loading direction is this way, I made the lap so the direction of the weld is perpendicular to my load. That is the weakest type of joint you can have, because now all the load actually carries in tension through the weld. So between those two extreme scenarios, you have a full range. So I do want you to see this chart just because it speaks to how your capacity will change depending on how the weld is being done. So the category, so this is fatigue. So what we're looking at here is the allowable stress. It's not the failure stress. It's what you can put on the structure and meet the code. And this is the number of cycles that you expect to happen during service. So if we're thinking about something that will have a little bit of vibration, say we go to all the way to 20 million cycles, when we pretty much have a constant value of stress that we can follow. So if you don't have weld on your structure, the code will say you can put about 23 KSI of stress in the material. Even if it's a cyclic stress, it's going to be fine. Now, as you start going into different categories of welding, all the way to the one I mentioned here, where everything is loaded perpendicular to the weld, your 20, 25 KSI becomes 2.5. So that is a factor of 10. To some extent, we were talking a little bit about plastics earlier in the class. The plastic can take this. In terms of a cyclic load. So you really, really went way down in your capacity. And here's some of the reasons why. Do you have residual stresses? Now, why do we have residual stresses? When it's easier to see on a butt joint. So we'll go back to this one here and assume for now that we're welding this entire zone all at once. So this becomes melted. It's very, very hot, and it cools. So when it cools, this zone is going to shrink as opposed to the material surrounding it. So there are two things that happen. The first one is distortion. It will bend this way. And the second one is internally, the reason it bends is there's a driving force. There's tension here on the surface that needs to be accounted for. If you have pre-tension, then you know that your capacity is going to be reduced in cyclic loading because you already, sometimes you can be very close to the yield strength on the surface here. So if you're already close to yielding, any force gets you over, and then you start having this accumulated damage very quickly. So there's a lot of analysis done in terms of what happened to the residual stresses. We're looking here into different directions. Probably the most significant one to think about is, let's see here. That's at the beginning. That's at the end. You do end up with tension in the direction here of the welded bead. So the idea that when you have the weld like this one, that you have a full capacity if you load it this way is not true either. You still, if I take this weld, this plate, and I load it this way, there's a likelihood that I start a crack right in the middle that goes transverse. So that would be a category B or a category C because now it's the tension in this direction that's causing me a trouble. But the tension that is the most problematic in general is this one here just at the toe of the weld. From the shrinkage here, you get the surface tension and it gets very close to yielding. If your structure, like a building, is getting loaded once, then what it means is for a little bit amount of time, you will need the ductility of the material, and maybe you'll need to get a couple % strain. That's all you need, and then it's done. That won't be a problem. But if you try to go back and forth in that zone is where you get the fatigue. And we could go through that in more details, but it's pretty, it gets complicated very quickly. Now, the last aspect, so we talked about residual stresses, we talked about stress concentration. The third thing that affects the strength of the weld is this heat affected zone. And we talked about it a little bit on Monday. You guys know where it is. You know for steel, it can mean an increase in strength, but a reduction in ductility. If we go through that Martensite phase, then we get into much lower ductility. So it's a place where cracks do tend to initiate, but this is for completely other reasons than residual stresses or the geometry itself. Is you change the material permanently. So between those three factors is where we get our factor of 10 if we're loading transversely. In general, now, is it always 10? No. 10 is essentially what AWS does, so we all understand. They provide you one chart for all grades of steel. It doesn't matter. If you have a higher strength steel, essentially they say it's going to become weaker than if you start with the softer steel. So it probably, if we know the stresses are going to be at the welds from a design standpoint, it means I don't even want to try to purchase, relatively high strength steel because my capacity here by code is exactly the same. And, there are reasons for that. Okay, so welding of relatively more aggressive structures. So here's an all-terrain vehicle. They're not all done this way. This is Bombardier, and you can see that there's a lot of bolts in this design. It's great for for repairs. Because you can take, if the front gets damaged, the upper part here, you can take a few bolts out and replace that component. I've seen a lot of frames that are single piece. So if you bend the attachment to the control arm, you have to replace the entire frame, take everything, all the accessories out the frame and do it again. So there are advantages. There's a compromise essentially on how many joints you're going to have. The advantage of welding in the shop is they have all these rigs where they position all the components very precisely, then they run the weld and it doesn't move anymore. It's done. It's quick, and it's subjected to this risk of burn through, so they can't make a weld this way. They don't want to make one this way, so it's somewhere in between where the trade-off is. And it's relatively difficult to control that welding quality. They will have robots that they keep track of. So even the robot cannot necessarily consistently make it right. So they have to have a look on it, and there are some joints that they do themselves by hand. So it's a pretty large industry, and I haven't been in an automotive shop, but I have to assume that it's a little bit the same way. They have to position the pieces and do a number of joints at the same time. They do sub-assembly, then they put it together, and then the overall dimensions are very well controlled. So that's how you keep your alignment, and you don't need the adjustment essentially. Okay, the type of steel here again is relatively low strength because you don't want your heat affected zone to be a problem. So we were talking about HSLA a little bit, high strength, low alloy that doesn't get into the martensite zone when you weld it. So that's the type of steel that you'll use for this. It's about twice the strength that you use for steel in a building, approximately. I showed you an image of this kind of butt joint that was done for pipes last time. I want to go through a completely different situation here of a chain. So let's see if I got the slides ready. Yes. Not this one. Good. And I have to redo this. So it's a little easier because I've been to this factory. We don't need the... one thing that you'll see here that is when they form their chains, it's done cold, so the steel is not hot. They don't do that for every grade of steel. I think they just picked the machine that was looking the more sophisticated and going the fastest. So you start with a rounded bar. You see the rounded bar threading through, and then they bend it one way, then they come and they bend the other side, and then they bring it to the flash welding machine. So what happens during the flash weld, the first thing that you see these two electrodes. So we have the two electrodes here that essentially provide the current all at once. They keep pushing on the chain, so any melting essentially gets the material to flow. That gets you all the impurities out because you don't have a slag here. This all happens very, very quickly. There's no filler metal, and you're left with an excess metal that needs to be grinded off, just like we had on the pipe on Monday. We talked about quenching, but I figured even if it takes a minute, may as well see it. So after the welding, they have to go through a furnace. It's a continuous process. So the chain is moving to a furnace, gets heated continuously, and then dropped into a bath. So what happened there is you are raising the strength, and then it doesn't, at that point it's less important, but they do reheat it to temper and reduce the hardness. Now, one reason I had to go to this facility is they did have a problem. So this is a chain that was used for deep water oil and gas production. They essentially have all, on the ocean floor, we have to clean this up. They have an entire system. When after the drilling, everything is completed for production, they have an entire rig system. So say that you have the wellhead, you have a lot of equipment here. And if it's not a very solid bottom, what they do is they put this equipment in tension. So they have a chain here that's connected to large buoyancy cans underwater, pretty deep at the corner. And the chain that were manufactured was essentially to hold that tension, to keep everything straight up. The chain is only as good as its weakest link, right? So one of them broke, a little bit like your carabiner. One side and then the other side lets go. So there's only one weld. If you remember the process, we started flat and we bent it so the weld was over here. And you can probably see it looks a little flat, just generally speaking. So we already know, oh, yep, it somewhat has to do with the welding of the chain. Looking a little bit more closely, we see this big crack arrest line right here. So I can't tell you at this scale that we see a lot of crack propagation line. I mean, there may be a few here, there may be a few there. So anyway, I do know that the initiation was in this area. So it started from one side and went to the other side. Okay, so from what we've learned so far, it means, well, there may be a bending load, maybe, or a material defect. So this is one example. If you look closely, well, yeah, there's something with the material here that definitely looks different than beyond that. So the first about 6 millimeters of propagation through this chain is different. So we went on, did some analysis. There were some secondary cracks. Here's what I wanted to show you. So going through the cracks, you see these. This is a polished section, and the crack is here. And we did put the pieces back together in this case. After looking at them carefully, it was just one side of the fracture. So you see these circles, right? These are the heat affected zone. So what happened is they were doing the big flash weld. It didn't work correctly. And then they went back to do some manual welding to repair it. And it failed at the manual welds. So we did some hardness through this and essentially found that the hardness in these repair welds exceeded that 35 Rockwell C I mentioned for stress cracking, environmental cracking. So after the fact, I think that the manufacturer admitted what they did is they did the repair weld after all the quench and tempering. It's completely unacceptable. Had they done it the other way, no failure. So the problem really is that they had essentially martensite in the final product, even though the entire process was built around avoiding it. So it's very unfortunate, but I figure this really ties into or deformation or welding and the impurities, and you get it all in here. Any questions on that one?
What should they have done?
They should have inspected very carefully before they heat up the entire chain and do the heat treatment. So if they had any repair to do, they would have done it then. But their internal process was more to do the inspection just before shipping it. And then, we have a problem. Well, do we want to just reheat the entire chain? They could have done it. So there are two ways. One is you inspect and you fix it before you quench and temper. The other way is after you repair, you redo the quench and tempering. It's not that hard, and you avoid having this weak material. But this is an example of weld-loaded in tension. It wasn't supposed to be cyclic load. This is just because it got too hard that the environment started to matter in terms of the strain. Thank you, guys. So tomorrow we have a guest lecturer, I believe. Yeah. And then Friday, Professor Eager. Monday, Professor Eager. I'm coming Tuesday, Wednesday, Thursday next week. I'll send the email.